and I want to introduce you to a new project we started with in collaboration with Oxford University E-Research Center. This is fairly new project, so the results I will be presenting are preliminary. And we, from Opava side is me, Karel Adámek, Jan Novotný, and from Oxford side is Wes Armour and Aris Kartaj. I hope I pronounced his name correctly. So, short version of this talk is that we are implementing Polyphase filter for Artemis project and Astro-Accererate project based in Oxford University E-Research Center to be used on radio signals from low-fi detector. You might ask what is Artemis, Astro-Accererate, LOFAR, and what is Polyphase filter. So I will try to answer those questions. So I'll start from what is radio astronomy. Radio astronomy is a job where you observe the sky in the radio part of the electromagnetic spectrum, and there is plenty to see. You can observe pulsars, which are magnetized rotating neutron stars, and pulsars are one of the main focuses of LOFAR and SKA detector. SKA even wants to use the pulsars for detecting gravitational waves, basically using them as one arm of the detector. And another thing we can observe are RRATs, which is rotating radio transients, which are short bursts of short radio pulses. And then we can observe quasars, AGN, and supernova remnants, and more. So, what is LOFAR? LOFAR is the largest radio telescope in the world. It's based in Holland, but it was spread to other countries like Germany or UK and France and Sweden. And it is the UK LOFAR station where our code should be employed. And what is important about LOFAR is that, that it is a software telescope. So the directing, well, LOFAR is omnidirectional telescope, but it can be redirected by software to look at a certain part of the sky using aperture synthesis. Basically, it considers only signals with particular phase. And this, another part of the software telescope thing is that the signal processing is completely done by software on off-shelf hardware and not by the specialized hardware. So, Pathfinder is also used as a pathfinder. Well, LOFAR is used as pathfinder for SKA, and SKA is a new radio telescope which should be built between years 2016 and 2033. It should be operational, fully operational in year 2004, and it's supposed to have 50 times the sensitivity and 10 times the survey speed than its predecessor. But these features are not cheap. The processing from SKA telescope will be very demanding on computer power and bandwidth. And for example, data from a single SKA dish will range in, it will be 160 gigabytes per second for a single dish. And from a whole SKA detector, it will be in petabytes per second, which means this is a transfer rate of 100 times more than today's internet traffic, which is quite a lot. And right now, we don't know how to, in real time, process such amounts of data. The another problem with SKA is that it's supposed to be situated in radio silent areas, which means usually deserts, and there is lack of power in deserts. So we need fast algorithms on low consumption hardware, and these things don't usually go together. So, and what's Adámek? Adámek is a group from Oxford, which tries to develop and use software for real-time analysis of data to discover pulsars and fast radio bursts using many core technology and intelligent algorithms. This is vital because from SKA we cannot store such amount of data, so we need to select the interesting parts of data in real time in order to store the interesting parts and throw away the boring parts. So fast algorithms and precise algorithms are needed. What we are doing is this part, channelizing raw complex data using polyphase filter. So what is polyphase filter and why we should bother? Well, in the end of the day, what we want is observe frequencies, but the telescope observe data in time domain, so basically some voltage from the detector. In order to get frequencies, you need to apply discrete Fourier transformation, which you can see here. This is our time data, small x, and this is frequencies which we will get from discrete Fourier transformation. The problem is with discrete Fourier transformation, or DFT, is that it has its drawbacks. And one of the drawbacks is DFT leakage. Another could be, for example, DFT scalping loss. So what's, I should say, why we use the polyphase filter? It's mainly because of these two things. And what is DFT leakage? DFT leakage is basically smearing of one of the frequency bins. Well, I should say it, yes. If you have a frequency in your signal, and it is not exactly in the center of one of the DFT frequency bins, it will get smeared into another bins. Because here the graphs are not very readable. I've used this. So this is our signal in the time domain. This is time, this is some magnitude. And this signal has, this is basically a sine function with frequency outside one of the DFT frequency bins. So what we will get from our DFT transformation is something like this. This is the bin where the frequency is, but the problem is that we get these lobes here and here, and we don't want those because these lobes basically spoils our data, and that's highly undesirable. So when we apply the polyphase filter, we get something like this. So we get a clear peak, but the problem is that the DFT leakage is still there, but it's very suppressed. So this is something, you can see it's from about 6 something here in magnitude, and noise generated by DFT leakage is about 0.010. So polyphase filter is good. Now, what is polyphase filter? Polyphase filter is basically a linear filter, and we can divide linear filters into 2 big groups. And one is FIR filters, and second group is II filters. But the main difference is how they respond to a single impulse. So this is our, well, This is what I've drawn. This is our single impulse, and this is a response of a FIR filter, which means final impulse response. And this is a response from IIR filter, which means infinite impulse response. And here you can see the main advantage, in my opinion, of FIR filter. This is that the response of FIR filter is finite in time. So if you get some kind of massive error in your real-time data, you will have some bad data in the end, but it will not spoil all of your data. So, mathematical prescription for FIR filters here. And I forgot to say what is Polyphase filter. Polyphase filter is basically applying FIR filter on n number of channels, where the n is order of your DFT transformation, which basically tells you how precise is your frequency scale. So more n means more precise frequency measurements. Also, another good thing is it is simpler to implement, but it's more computationally demanding. And now there's my part in it. What I was responsible for is doing vectorization and intrinsic on Intel processors. What vectorization means? Vectorization is basically converting your algorithm from scalar approach, which means that a single instruction operates on a single number, to vector approach, which means a single instruction operates on vector, which means multiple pieces of data. And intrinsic is basically a convenient way how to use assembly instructions in your C code or Fortran, it doesn't matter. So here's my preliminary results. This is a serial implementation, which is slowest. This is time, and this is the size of processed data. And you can see that parallel implementation can sometimes be slower. That's because parallel implementation has its own overhead, which is not in serial code. But as you can see, in the end, in a large number, large data files, it's considerably faster. And here are some implementation of my intrinsic code. You can see I've done a lot of them. And it's good that my final implementation is fastest. So, and what I should say is one of the important parameters for your program is bandwidth. And in FIR filter implementation is extremely important because FIR is bandwidth bound. This means that processor can compute enough numbers, but you are not able to push enough numbers from your memory to processor. That's why it's bandwidth bound. And my last slide is that how many threads you should run your code. It's not that simple because, as you can see, there are several minima, and it's always depending on number of threads you run. And, this analysis is always good to do because you never know what the answer will be. As you can see, this is 24 threads. This is about 12 threads. But a strange result is this. For example, 4 threads. It's not the fastest, but it shouldn't be there, basically. This graph must be tied to whatever machine you run your code on, because I run this code on Xeon machine with Xeon processors. It has 2 processors with 6 core each, and each core can process 2 threads. So it should be basically fastest on 34, which it is, but it's not always so. And the future work is to port the existing code to Xeon 5 processor, which is basically number of Xeon processors put together and stuck into the card which you can put into your computer. Oh, that's all. Thank you for your attention.